Decadal variability is a difficult issue, and it's important, and so that's under motivating questions, so I'll just do that. And then just talked about some old tools and why they're kind of problematic in terms of understanding decadal variability, and show you a new tool that I'm really excited about, and maybe where it will lead us. And we've done a lot of work on this in the last 3 months. It's just like all the pieces are falling together really fast, so I don't know if I have a complete story, but I think it's a really exciting way of looking at decadal variability. This is all from data. I don't think I'm going to show you any model results today. It's all from data. So the motivating questions are, what are the patterns and physical mechanisms of natural variability? I mean, that's on decadal timescales. I mean, there's an interest in that. Like around here, I think the decadal variability actually does have ramifications for society. In the North Pacific, I'm sure it has ramifications for fish, but I'm not so sure it's got ramifications for society. In the North Atlantic, there's a little bit of a decadal signal that may or may not be predictable. But what are the patterns and what are the physics behind them? We almost know nothing. We have land observations that go back 100 years. We have observations of sea surface temperature that are great in the North Atlantic for 100 years, and they're okay for 50 years. What's that?
No, I'm just trying to...
It's too dark?
Remote control.
Too dark?
It's too dark.
No se puede cambiar más.
It's either dark or...
Sorry.
Okay. All right. And of course the other reason why we want to know this is like where we're seeing these global changes, but what fraction of the changes, what changes are actually anthropogenic and what are natural. So here's one way you can do global warming. If you want to, you can take the global average temperature and you can just plot a time series of global average temperature. That loses a lot of spatial richness in what's happening. Okay, so you lose spatial information. For example, which basin is actually doing most of the warming? Is it the tropics? Is it the high latitudes? Another way you could do it is you just look at the linear trend, a spatial map of linear trend, which gives you some idea of the spatial structure, but it's linear. So there's no like bumps, that are obviously there, and some of the bumps might be forcing like changes in aerosol distributions due to human activity, and some of it might be real bumps that actually are associated with the warming signal. So you lose temporal information here, and also we expect that the warming is going to be really rapid in the tropics, in the sense that the tropics feedbacks are fast, but the mid-latitude feedbacks and high latitudes are slower. So you lose that richness when you put a pattern like this in. So the traditional way you do this is like you do EOF analysis, that you kind of organize your information because there's just too much information, and so you reduce the degrees of freedom, and you just take a principal component analysis, EOFs. I think in geology this used to be called factor analysis, and in social sciences I think it's still called factor analysis, if I remember. It's the same technique. It's just a way of organizing. It's the same exact technique, just different names for different fields. And so, principal component analysis considers spatial and temperature variations. It does not depend on time scale variability, so it doesn't actually do anything special with time scale. And of course, it's subject to the constraints that the patterns and the time series are orthogonal, which is really unphysical, right? So it's not it's like nature doesn't do that, right? Even a drum head will do that. And if you took EOF of the drum response, you actually do pretty well. They do actually describe physically what's going on, but that's about it. In fact, you can actually show that in any geophysical system where the fluid has a shear or a mean state that's not uniform, EOFs can never capture physical modes of variability. It's mathematically impossible. Okay, so it's just an approximation of just like, how do I get my hand around this? And for the Pacific decadal oscillation, the way that was originally defined is it's just the first EOF, the first principal pattern of sea surface temperature in that box there in the North Pacific. And how the rest of the map is filled out is you get your pattern, which is the pattern in the box, and then you project it onto the data, and you get a time series, and you take that time series and you project that onto the world sea surface temperature, and you come up with that map. Okay, so is that, let me see, if I hit the red button here, is it going to point, or is it going to turn it off?
It should be a pointer.
Should be a pointer? Oh, it is. All right, good. I should have just tried it. You got to live life, right? So that pattern actually comes out of the analysis in this box. And that pattern you can see has all sorts of time scales in it. Interannual, in fact, if you look at that, there's as much interannual time scale in that as there is decadal time scale. But it's called Pacific Decadal Oscillation because it seems to go into like it's positive for this decade here, and it's negative here, it's positive here. So you can see decadal stuff here, but there's a lot of interannual there. Okay, so this is the PDO, the traditional way of defining it, first principal component of North Pacific SST. And if you look at this pattern, you can see it looks like it's actually maybe due to the tropics, right? You can see a lot of activity here in the tropics is just as red, deep red here as it is deep blue here. You know, so it's like looking like a tropical thing, maybe forced out of the tropics. It's got decadal and interannual time scale. It's strongly correlated with El Nino index if you look at Nino 3.4 or Nino 3 or Colton index. And then you can do the same thing here. You can do the EOF analysis on SST in the whole Pacific Basin, and you come up with this pattern, which is ENSO. And there's a time series, and you see it's mostly interannual time series. Okay, it's the first principal component of SST in the entire Pacific, and mainly interannual. Okay, so why is this a problem? And you can see it right away here if you just take the principal component analysis of the whole tropical Pacific SST and just put the first three on the page. So here's the first three. Now we're going to do it. So it's basically back at this picture here. We're just going to look at all three of them. The first three. So here's the first three. You can see the first one here. What's that? El Nino. This one, well, looks like the hiatus, kind of a little bit, you know, maybe. And then this thing here, it's like the north. It's like maybe the PDO, maybe not. There's a lot of stuff on here. It's starting to mix these things up physically. I mean, they don't make any sense, right? So, and that's why you draw a box, because people realize that there's something special going on in North Pacific, so they do the box there. Right? And we know something special is going on in the tropical Pacific, so we draw a box there and we take our EOFs. But if you just do it on everything, you start getting this mode mixing. So if I look here, okay, global warming is in this one and this one. See the trend? Yeah. Warming trend. So it's mixed the global warming signal up between two EOFs. If you look at the PDO, it's actually a mixture of this and that. You can see there's definitely low frequency stuff here, there's low frequency stuff here, so it's kind of scrambled things up. It's not a good approach here. So where is the decadal variability? It's kind of in all three of them. Okay. So can we do a better job of separating these patterns of variability based on their spatial patterns and their temporal time scales? Okay. So here's another reason why you're getting something physically unrealistic when you do EOF analysis. So this is just a regression of sea level pressure on the Nino 3.4. So this is the ENSO. We'd take the ENSO signal, and this is just regression. So this is all time scales. It's interannual, it's decadal, everything's in here. And then here is the sea level pressure regression on the traditional PDO index. And one thing that comes out here, which is really strange, is if you look at the regression at the Nino 3.4 value here in the PDO with the sea level pressure, say up in here, Aleutian low, you find out a 0.25, if it's really the tropics driving the extratropics, a 0.25 C anomaly in the tropical Pacific here drives a 1.5 hectopascal sea level pressure anomaly. Okay. Then you go to ENSO and you say, well, a 0.8 degree C, 3 times bigger, drives an anomaly that's only 2/3 as big. That's physically unrealistic. I mean, there's no reason. So you end up with this kind of strange thing that you have a physically unrealistic amplitude teleconnection on the 2-time scale. So there's clearly something wrong here in terms of attributing these things to the tropics. Okay. So here's a new, that's the problem with the old tools. A new tool is called low frequency component analysis. So it's still taking all your degrees of freedom and kind of boiling it down to just a few patterns. And I'm going to show you an example today of the application of this to the total Pacific sea surface temperature observations. Okay, and it's a generalization of this thing called the signal to noise maximizing EOF analysis, which has been used in signal processing, for example, transmissions of telephone signals for a long time. It finds the linear combination of EOFs, so it's still an EOF analysis, that maximizes a particular type of variance, representing a signal, your choice of what you want to call a signal. In this case, we're going to call our signal decadal. That's what we're interested in, decadal variability, compared to internal noise. In this case, our noise is going to be really the interannual stuff, because we actually know what that is. And we know ENSO, for example. We know mid-latitude storms. And you can use this mathematics for a whole bunch of things. One has been used in literature to maximize the variance that is robust across models. You can use to maximize the predictability, and there's some references here to do this. You can use it to maximize the variance between decades, and that's kind of what we're looking for, because we're actually looking at decadal changes. So we just have actually a simplification of that technique that was put forth by Tapio Schneider and Isaac Held. And it's what we're going to do is maximize the ratio of low frequency variance to total variance. So we're going to still find patterns of variability, leading patterns of variability, that maximize the amount of low frequency variance that's captured in those patterns. Okay, so we call it low frequency component analysis. So this low frequency component analysis picks out patterns that maximize the ratio of low frequency to total variance. We call that ratio R. It yields a series of patterns in order of decreasing R. So the first pattern is going to explain most of the decadal variance. And the second pattern will explain the next one. And if you have 25 EOFs that you're using, the 25th pattern will explain the 25th ranked decadal variability, which turns out to be ENSO, actually. Not surprising. If you look at the Unidos 3.4 index, the variability at low frequency timescales has very little variance compared to interannual timescales. Okay, so the time series of the patterns are orthogonal. That's a nice convenience. And it takes advantage of the covariance of data on all timescales. So you actually calculate the EOX on the total data set, but then you filter the data set and you project them back on combinations of those EOFs that explain the maximum low frequency variability. It's actually not a complicated technique. You can do it in MATLAB in about 5 lines. Actually, I think 2 lines. You can find the pattern explains. Oh, you have to do the filtering, so it's actually 3 lines. Okay. You can find the pattern explains little of the low frequency variance. So actually, this technique, one of the EOFs that'll pop out of here might have a tiny amount of decadal variability, but all of the interannual variability, and that actually does happen. So one of the EOFs that pops out is ENSO. It explains almost no low frequency variance. Okay, so here's the application to the Pacific SST, 1900 to 2016, 45 south to 70 north. And there's some choices you have to make here. One is how many EOFs of the total data set are you going to use to start with? As an example here, I'm going to show you we're only going to keep 3 to start with, but then I'll show you a picture that shows 25 EOFs. So how many EOFs are you going to retain when you do this analysis to maximize low frequency variance in all of the EOFs that you've kept? And the other one is, well, you want to say low frequency, you maximize low frequency. So what is the low frequency? We're going to just put a 8-year low pass filter on this data set. So we're grabbing things that are on time field of basically a decade and longer. Okay. You get new patterns of variability are found by projecting the filtered data onto the EOFs and weighting that maximizes this ratio of low frequency to total variance. And then you get the time series by projecting those patterns that you get out of it onto the total data. Not the filtered data, but the total data. And the time series of the patterns are orthogonals, but the patterns are not. Okay, so this is where here are the first 3 components. They're the equivalent of the 3 components I just showed you before with traditional UF analysis. But this is saying, give me the 3 patterns that explain most of the low frequency variance. And we're only retaining 3 patterns, 3 EOFs in here, so this is actually all the variance. These 3 things explain all the variance in the record. The first one is this. It's a kind of a not uniform warming, but it's warming everywhere in the Pacific. And you can see, boom, like there it is. There's the global average temperature rise. And this is the Pacific contribution. And it's not homogeneous. It's spatially kind of rich. The warming is maximum up in here and maximum down here. if you go across this record here and you average over the whole Pacific, it's about a 0.8 degree warming. So it's a little bit less than the global average over this time period, but it's a pretty big contribution since the Pacific is like half of the world. Okay. So you get a higher signal to noise ratio than the Pacific Basin mean. So if I just took the average over the whole Pacific, what the temperature is, and just did show the time series, it doesn't explain as much low frequency variance as this pattern does. So this is giving you kind of a richness in what the warming pattern looks like. Okay, the second one looks like this, and believe it or not, this is the PDO. Okay, so there's the cooling in the cooling in the Eastern Pacific, warming up here. You get a little warming here. Here's the time series, and if you actually take this time series and you correlate to the traditional PDO, you get 0.95. So it's basically the PDO. Okay, and the last, we'll call this PDO star because it's not the traditional way of defining PDO, but it's PDO star. And the last one is this, which everyone recognizes, right? Beautiful, and look at the time series. There's like very little low frequency variability in that. Right? It's all interannual. It's correlated at 0.89 with Nino 3. It's more equatorial confined than if you take Nino 3 and just regress it against sea surface temperature. Everywhere. Okay, so this is called ENSO star because it's a different way of defining ENSO. So the notes here, the PDO star has more low frequency variance than the PDO. So if you're really interested in decadal variability, that's probably a better index of what's going on because it explains more of the low frequency variance. ENSO star has more interannual variance than ENSO. So if you're interested in the ENSO variability, this is probably the better index to use than, say, the traditional Nino 3.4. ENSO contains very little low frequency variability. If you look at the spectrum of this, it's pretty much all in the 3 to 5 day band. The correlation between ENSO and the PDO, if you use traditional indices, is 0.5, suggesting that there's a link between what's going on in the North Pacific and what's going on in the tropic. The link between ENSO star and PDO star, by definition, is 0. Right? It's saying that those two things are entirely unrelated. Okay, now they're not entirely unrelated, but there's not a lot of shared variance between these two things. You can think of ENSO as being pretty much separate from the PDO, where the PDO is kind of more of a North Pacific phenomenon. Now, it's not totally North Pacific. This is the thing there's some puzzling things that come out of this that I think are still really exciting. So there's actually, the other thing is that if you're interested in the global warming, there's actually no trend in either of these two patterns. It's all the trend is in here. So it really separates these things physically really much nicer than a traditional EOF analysis. Okay, so if I compare it to traditional PDO, this is a same thing. We're doing the same analysis, but now we've kept 25 EOFs in the data. And the technique is still going to say, I want to get most of the low frequency variance that's in those 25 EOFs, basically. And the pattern that pops out is this one, which looks a lot like the pattern I showed you before, only you've kind of really lost the tropical signal. If we go back here, so this is the pattern, right? It says cooling, warming, but I see this little bit of warming here. But if you do it on this, you keep all 25 EOFs, which captures a lot more of low frequency variability than the 3 EOFs did. You end up adding up something that looks very much like this is a North Pacific phenomenon. Okay. And that's the traditional PDO right there. And so you can see the difference is the traditional PDO index grabs tropical stuff. Okay, and then this is the time series. The black is the time series of the traditional PDO index, and the red is the PDO star, or this index here, multiplied by 1 on 0.6, just to give you the scaling here. And you can see that they're really similar, only there's more decadal power in the PDOs in this pattern than there is in this pattern. And that's simply because there is some ENSO that's actually driving PDO, but it's actually not low frequency ENSO variability. It's actually many interannual events in the same decade that give you a residual. It's not truly decadal ENSO variability. It's like you have 3 ENSO events this decade, 2 that decade. The difference is 1 ENSO divided by 10 years. It looks like low frequency variability, but it's not. This actually techniques separates that out. So why you lose this lobe here is because the stuff that's actually linked to the tropics is this high frequency stuff, which is and it's just the average over a decade. So it really suggests that the PDO has decadal physics. It's actually almost entirely separate from the tropics. Not quite. I'll show you there's some hints here. So it's largely confined to the extratropical Pacific. The point here then is this is the amount of low frequency variance explained by the traditional PDO. It's 32% of the variance in the whole record is decadal variability associated with that pattern. But 46% of the low frequency variance is explained by that pattern. So it's explaining much more decadal variability than the traditional one, 44% more. Okay. The difference, if you take the difference, you do two time series, and you get this time series, and you regress back on SST, boom, there's the ENSO. Right? And the time series you can see here, there's some decadal stuff in here, but there's a lot of interannual stuff in here. Okay, so it's starting to give you things that are much more physically intuitive here. Now, the other thing it does is it suggests that the PDO is more predictable than we thought. If this is the traditional index of the PDO, this is the autolag correlation of the time series, and you can see it falls off pretty fast, and it's basically 0 by 2 years. And if you just use the 3 EOFs, so you're mixing still ENSO in a little bit with the PDO, it falls off just as fast. But that last figure I showed you that just really isolates the North Pacific, it falls off pretty slowly. There's actually some skill quite a ways out. Some autocorrelation. So there's probably more persistence to the PDO than has been suggested in the literature. Okay, so it's probably more predictable. Now, the other thing is if you look at the relationship between ENSO, the traditional relationship, Nino 3.4, and the traditional PDO index, you can see it looks like, well, they're related here. At no lag, the correlation is 0.5 between the two. If you look at the relationship between ENSO star and PDO star, well, by definition, these are orthogonal time series, so there's no relationship at 0. There is this hint here that it may be 6 months or 9 months out, ENSO leads the PDO. That's basically the interannual ENSO stuff. 3 this decade, 2 the last decade. The difference is 1 per decade, and you average it, and it looks like low frequency, but it's a really weak signal. The correlation is only 0.2. The other thing is, this is puzzling. I don't understand this, but it just suggests that if you actually know the North Pacific variability, there is some lead. I mean, the PDO, in a sense, does have an impact on ENSO. It's not huge. I mean, these correlations are 0.1, but it's like 2 years in advance. So I don't quite understand that, but that's the result. So PDO is more independent of ENSO than is found with the traditional PDO index. A small fraction of the PDO is driven by ENSO. That's the residual of the interannual variability. That's this right here, this little peak. And then there's a suggestion that PDO star leads ENSO by 2 or 3 years. I don't really understand that, but that's where it's at. Okay. So then if you go back to this problem that we put out before, how do you explain the fact that the decadal teleconnections, if they're really being driven out of the tropics, are 5 times larger than the interannual ones? And the answer is you don't. Because if you look at the regression of PDO star onto sea level pressure, you see that this is mostly a North Pacific thing. Now this is the puzzle. It's mostly North Pacific. It's clear that the PDO, the North Pacific thing, has an impact on the tropics. There's like 2 years lead time. There's some relationship between what's going on in the North Pacific and what's going on in ENSO, in the tropics. And I guess that must be the link to the Southern Hemisphere. So there actually, according to this analysis, there is a link between what's going on in the Northern Hemisphere and what's going on in the Southern Hemisphere, with the Northern Hemisphere somehow driving this through the tropics. And then this is what you get for ENSO, and you get the kind of what you expect to see. You get teleconnections to both hemispheres. Here's the PNA pattern over here, and here's the PSA pattern, or whatever we call it nowadays. Actually, and the amplitude here goes down, and that's simply because some of this is actually really not. This is just the PDO stuff is then captured by the ENSO index. And actually, these numbers here actually are what the atmospheric GCMs tell you when you prescribe a sea surface temperature. So it's really nice. It says that the models aren't wrong. They weren't giving you the right amplitude in the first place because the right amplitude was the wrong amplitude. It was capturing something else. Okay, so the answer is they're not consistent. The PDO is mostly a mid-latitude phenomenon, and the traditional way of capturing these things is mixing these modes. Okay. How am I doing on time? I just have one more slide.
You have 5-6 minutes.
Okay, maybe I went too fast. I could show some more. We've done a lot of analysis on the Atlantic, which is kind of fascinating. So I'll just show you one slide here, because the Atlantic one actually is even more clear. This is the low frequency first component on the all Atlantic sea surface temperature. And you can see it's kind of like pretty much a global warming with kind of a rich pattern. Here's this, I don't know what you call it, a cold hole associated with basically really deep convection. So you're putting all this extra energy into the system, and you have to heat 4,000 meters here, and you only have to heat 75 meters here, right? So this is basically the global warming pattern. You can see it. Here's the time series. Boom, right? It's warming. There's a stall around, in the mid 1900s, and then it starts warming again. So that's that pattern. The second pattern is this one, which is the Atlantic multi-decadal variability. And you can really see it's tied to basically convection up here in this region, in particular in the Labrador Sea. But here's this hot spot, and here we go. Look at this beautiful multi-decadal signal. Now the cool thing about this is when you so the traditional way of defining the Atlantic multi-decadal variability is this kind of brain dead way of taking this box average sea surface temperature, and then you create an index of that, and I'll show you the index in a second, and then you regress it back on the sea surface temperature, which gives you kind of a rich pattern. That pattern doesn't look that dissimilar to this one. It's getting a little bit more subtropical stuff. And there's the time series, and you can see they're pretty similar. So this is grabbing the low frequency variability really well, whereas the traditional index mixes in maybe a little bit more interannual variability. The spectrum is a little bit, gives you more interannual variability, which you can see in particular in this decade here, where this is going all over the place, and this is a little bit more smooth. The nice thing then is if you actually take a climate model and you do the same thing, the CMIT-5 climate models, and we did it on, I think, 25 different models, this thing pops out in all the models, which is cool. And if you take this index, if you take this box average sea surface temperature models and you regress it against the overturn circulation, you get something that looks really strange. If you take this index and you regress it against overturn circulation, you get exactly what you expect. It's either speeding up the overturn circulation or it's weakening the overturn circulation in the models. So it gives you something really nicely physical, and apparently the models actually are reproducing the pattern that's suggested in the data, even though we don't know from data what the overturn circulation is doing. The models seem to be doing this pattern. Not all of them. There are some of them that give you warming in wrong places, but most of them give you that pattern. And I should say, going back to the model things, we've also done the analysis on all the CMIT models in the Pacific, and they all have the PDO. The PDO is defined as this mid-latitude phenomenon, and they all have really lousy ENSOs. It's not a surprise, right? We all know that. So the ENSO stuff doesn't come out, but the PDO actually comes out really well in the climate models. Okay, so last slide. Low frequency component analysis features distinct patterns and time series of low frequency variability that better illuminate the processes responsible for them. So I haven't gone into this, but actually you could look at your time series of the low frequency PDO, and you can regress it against, for example, surface fluxes from the models, in wind stress curl from the models, and you get this picture, which is not different than kind of Latif and Barnett postulated 30 years ago. You have more confined to the mid-latitudes and more independent of ENSO than previously thought. It's due to stochastic mid-latitude wind stress forcing on the ocean gyre, which spins up the ocean gyre or slows it down depending on the sign of the stochastic forcing. And then that gives you sea surface temperature anomalies in the Kuroshio a few years later, and the atmosphere responds to that change in the wind stress curl over the basin. Okay, so you get subsequent SST anomalies in the Curcio, which force atmosphere to have a weak negative feedback. And so you get